So last time we talked about some computer architectures. We use binary number to represent text, image, videos, and audios. And so everything in computer is represented as binary numbers. So just to review that, like if I have a 2-bit binary number and I can represent 4 things, and that's 0, 0, 0, 1, 1, 0, and 1, 1. Yeah, and for an image, there are red, green, blues, and they are all from 0 to 255, which needs 8-bit. This is 2-bit. And so one color is 8-bit, 3 colors is 24-bit. So that's for image. And for image, they are always like 0 or positive numbers. So far we only represent like positive numbers, but there are also other numbers that we haven't represent. So here I'm gonna tell how to represent negative numbers. So a very naive idea to represent negative numbers is to just add 1 bit for the sign. So for example, if 0 is positive, 1 is negative, and this is the magnitude, it's the same. It can represent 4 numbers, which is 0, 1, 2, 3 for these 2 bits. So this represents the sign. So there are minus 1, minus 2, minus 3 as well. Yeah. So on the odometer, like here is the 0, here is 1, this positive, and here is 5. 0 is positive, okay. And here is 1, 2, 4, 8, which is positive 15. And for here, 1 is minus or negative, yeah. And this is minus 1, this is minus 15. So this is the first method, which is very naive. It is called sign and magnitude. Just mean like 1 bit for sign and others for magnitude. Is this clear?
Yeah.
Okay, and there are some problems with this method. So there are 2 zeros, which is positive 0 and negative zeros. And also, if you look at the odometer, like if you only look at the binary number, like we know that when we go to this way, the number is actually getting smaller and smaller. But when you look at the binary number itself, it's this. And for binary number, it's like it's almost like it's going bigger and bigger. But for its actual value, it's going smaller and smaller. So this is not nice. That's why I say that like incrementing the binary odometer, sometimes it increase, sometimes it seem to decrease. And this cause very complicated circuit or hardware. And yeah, you can just ignore this first, and I'm gonna tell you this how to build like hardware to do all the calculation in maybe following lectures. But this method causes very difficult and complicated circuit. So people used to use them at some time period, but they finally give it up. And so people come up with something called a ones complement to like solve this problem. Okay, solve this problem. And so basically for positive numbers, I will introduce like 4 or 3 4 method to represent negative numbers. And for the first 3, the positive numbers are the same. So we only change the negative numbers. So for positive numbers, they are the same on the odometer for positive numbers. and the next one. Yeah. And so we only look at the negative numbers. And this is called one's complement. And maybe its Chinese name is nicer to like understand. It's called fanma. It's basically like if you get from, for example, +1 is 0, 0, 0, 0, 1, and -1 is just change all the 0 to 1 and all the 1 to 0. And you got 1, 1, 1, 1, 0. This is -1. It's here, yeah. And so this is +0, this is -0, this is +15, this is -15, very similar. And it still has 2 zeros. We haven't solved this, but we solved this problem. Like if you look at the binary number, it seemed to like increase with from left to right for negative numbers, and its actual value also increase, which is nice. But this also like lead to very complicated circuit. Is this clear?
Yeah.
Okay, so then people just give up this 2 and they come up with 2's complement. It's just it's solving the 2-0 problem, and they just like get all the negative numbers left by one step, and they get this. So there's only 1 0. That's kind of naive, but it really solved the problem. Like now it's the +15 here, and this is the -16. Right. This picture may be a little confusing. It's bad slide. So this for another figure, and only for the odometer here, and we got -16 to +15, and only 1 zeros here is here, and this lead to very simple circuit, and it can like you can do addition and subtract in the same circuit. You can just remember this. I'm gonna tell you in the following lectures. So this is called 2's complement, and nowadays most computers all use this, and nobody use the former 2 method. They are just like goes away, yeah. And so this is the 2's complement, and so this is just turning the odometer into a circle, and they mix the same thing. Yeah. So is this clear?
Yeah.
Yeah, and we go to, oh yeah. So there's another slide on 2's complement. Like it's interesting, like how to read this into decimal numbers, like from binary to decimal. And if you got 1101, and remember that like if it starts as 1, it's negative numbers. If it starts as 0, it's positive, and you can just delete the sign bit, and for the other bit you just do the like normal binary to decimal. Like if for this 1 is 1, 1 is 2, 1 is 4, 1 is 8, right? And we can say it's +8 plus 4 plus 2 plus 1 is +15. And but for like negative, you cannot do this. You should not delete the sign bit, and like here you multiply it as -2 to the 3, and add all of them, you can get the decimal number. Yeah. And another interesting thing is like if you want to go from +3 to -3, like and then to +3, like you want to go from one number to its minus, like from firstly from -3 to +3. So we see here -3 is 101. So this means like turn all the zeros to 1 and all the 1 to 0. So here 101 is turns into like 0, 1, 0, and add 1. So this is like first get its ones complement and then plus add 1. That's how you go from negative to positive. 或者说是取反加一，就是把所有的零变成一，一变成零，这个叫取反。然后加一就是直接加一。Yeah, so basically here -3 is 1, 0, 1. We do the ones complement and get 0, 1, 0, and add 1, we get 0, 1, 1, which is positive 3. And similarly, we go from positive 3 to negative 3, it's 0, 1, 1 here, 0, 1, 1, and we do ones complement, it's 1, 0, 1, and add 1. Oh no, it's 1, 0, 0, and add 1 is 1, 0, 1, and we get negative 3. Okay. Is that clear?
Yeah.
And so for this case, it's only 3-bit, and this is 4-bit. There's no difference, and so this can represent a larger number than this. Yeah. Okay. So the fourth method is called bias encoding. This is the most straightforward one. Like I say you have like 0, 0, 0, 5, 0 to 5, 1. So this is 5-bit. And for originally, there's only positive numbers you can represent. 0 to what is 5-bit? 5, 1. 5, 1 is 31, I think. So we just do a bias and we just minus all the numbers with some value. Like for here, we get them to like -5 to, okay, we get them to -15 to +16. So we just minus, just subtract all the numbers with 15, and we got this, right? And this is called bias encoding. So you see here, all 0, it used to represent 0, but now it represents -15, -14, and this becomes 0, and this is +16, I think. Yeah, maybe. Yeah, I think that's right. And so this is called bias encoding. It's just, so for 2's complement, like it's sort of complicated. So positive is 0, negative is 1. And for here, like it's like positive is 1, negative is 0, but this do not mean sign anymore. This is only this is a like separate method called bias encoding. So people only use 2's complement and bias encoding. And unsigned is the last lecture on like represent positive numbers only. Yeah. So we only use these 3, therefore negative numbers. Is that clear?
Yeah.
Okay. And we still got other numbers to represent, like, so one of like if a number has both integer and fractional parts, like 1.5, they have a point inside. So we still cannot represent this, and also very large numbers and very small numbers. And for example, like if you have 32, anyways, let's move on first. And so how to represent like a number with a point inside? So a very naive idea is to like we fix the point here, and So this is 2 to the 0, this is 2 to the 1, this is 2 to the -1, this is, yeah, something like this. And so here are 6-bit, and we can, like, if 10.1010 is basically, this is 2 to the 1, this is 2 to the -1, this is 2 to the -3, and add them, we got, in decimal, this is 2.625. And there are 6-bit in total, and the point is fixed, and we can only represent 0 to 3.93675. This is actually a very small range, and so remember, for unsigned or just positive numbers, for 6-bit, we can already represent 0 to 2 to the 6, which is a very large number. But for the fractional number, or we only represent very small range, which is not nice. And another problem is, like, if you like, for example, 1.1 and multiply 0.1, so they are both like fixed point at, so they are 2-bit, and the fixed point is at here, and if you multiply them, then we got 110, which is 0.11, and we got another fixed point, which is 3-bit, and the point is here. You kind of have to memorize where is the point, because it is like set fixed in the binary number. So this is kind of difficult. Like you are basically going to another method to represent like point numbers when you do a multiply. Is that clear?
Yeah.
Okay, so we just do not use this. This is bad method, and we use something called like floating point. What is a floating point? Like, contrast to fixed point. Floating point is like the point can go everywhere. It is not fixed, like this or this. And we use scientific notation first. What is scientific notation? So you may be very familiar with this in decimal, like 6.02 multiply 10 to the 23, and like 3.3 multiply 10 to the -10. This is also a scientific notation. There's only one number behind before the point, and all other numbers are after the point. This is called scientific notation. Yeah, and this is in decimal. In binary, there's only 1 and 0, and this becomes 2. Okay, and so we use this to build the floating point. So remember that if I got 1 point, I also got 1.1101. Like, this is also a binary scientific notation, and also 0. Yeah, also 0. And so if you look at it, like, all the numbers except 0, their first bit is, so the bit before the point is 1 for all the number except 0. Why is that? Because there are only 0 and 1, these 2 digits in binary. So unlike like here, you can be 1, 2, 3, 4, 5, 6, 7, but in binary there's only 0 and 1. So except 0, all the number before the point is always 1. Yeah, so we can like somehow set it as default, like, because we want to so the main idea of binary binary, like floating point is like we represent this and this separately. Okay. So let me show you this first, maybe. And this is the sign. So like 1 is 0 and 1 is negative and 0 is positive. And after that, other 8-bit is like exponent. Exponent is this stuff or this stuff. It's exponent. We use this to represent the exponent and this to represent the significant. Yeah. And you must heard that something called 32-bit computer or 64-bit computer, or in Chinese 32位计算机 64位计算机. So this is basically saying that we have totally 32 bits here. So we are doing 32-bit computer here, and there are in 32-bit computer, 1 is for sign, 8-bit is for the exponent, and 23-bit is for the significant. Yeah, is that clear?
Yeah.
And the reason why we like set here we set the 1 for the default and all the other bit only to represent the number after the point is that we can save 1 bit here. If we save 1 bit, then this can represent 1 more bit, which is a larger range of numbers. So we kind of want to save 1 bit here. So we set the 1 for default. Okay. Yeah, because except 0, all the other number is always start with 1. So we just set this for default. Yeah. And at the same time, we like if all the exponent is 0, then it represents 0. Yes. This is a little weird, but it will be clear later, maybe. So again, in this 32-bit, and this is the exponent, which is 8-bit. This is significant, which is 23-bit. And this is the sign, which is positive or negative. Yeah, so in this way, it's very magic, and we can represent numbers from, like, what is the smallest number? Like, if all the significant is all set to 0, 23 0, and this is set to, let me think. This is set to, so 8-bit can represent 0 to 255, right? And here's we actually use bias encoding because exponent can be positive and negative. So here we use bias encoding, which is the fourth method here, right? So we just subtract it and let it to represent -127 to +126, right? Is that clear? Yeah. Okay. And so, +128. So it's here. So 8-bit can represent 256 numbers, and here we just from -127 to +128, which is 256 numbers. And actually, we only use -126 to +127 because the last one and the first one are reserved for other use. I'm gonna like tell you later in the lecture. And so we only use -126 to +127. So this is for exponent. The range is from -126 to +127, and for the significant, the one is for default here, right? And we represent 23-bit here, which is from all 0 to all 1. This is the range of significant, and So, and there's also a sign. So we can, so we only consider positive, like the sign is 0 here. The sign is always 0, which means positive here. And so what's the smallest number we can represent in positive numbers? It is 1.00 and minus 2 to the minus 126. This is the smallest number. Is that clear?
Yeah.
Okay, so for the largest number in positive, we can represent 1.01 multiply 2 to the positive 127, right? Yeah, this is the largest and this is the small. This is the smallest, this is the largest. Yeah. So the smallest number is here. And when we change it to like decimal, it's like 1.2 and 10 to the minus 38. And when we change this to the decimal number is 3.4 to multiply 10 to the 38, which is a very, very large range, right? And this is very nice. So this is the floating point. It can represent very large range compared to like fixed point. Okay. And just to remember that for the significant part, the 1 is set for default, so all the significant is from 0 to 1. Okay, is that clear?
Yeah.
Okay, this is maybe a little confused. So what is this? It's like for all the 1, like for all the 1 here, you're basically, this is 2 to the minus 23, this is 2 to the minus 1, this is 2 to the minus 2, right? And you are basically doing, there are 23 bits in total, and you are doing 2 to the minus 23 plus 2 to the minus 22. There's all ones, 22, and all the way to 2 to the minus 1. And this stuff is equal to 1 minus 2 to the minus 23. Is that clear?
Yeah.
And this goes to here. And the 1 is for default. And multiply the exponent. Okay. Yeah, that's it. And so to get a deeper understanding of how good the floating point is, we can like do some contrast here. Oh no. So if we got 6-bit fixed point, here 6-bit fixed point is from 0 to like almost 4, right? But if we got 6-bit like floating point, and for example, we got 1 sign and 2 exponent and 3 significant, which is totally 6-bit, right? And anyways, and so this is 6-bit, and we can represent what? Like here, exponent, we can represent 1, 2, 3, 4. Oh no, maybe of minus 1, 0, 1, 2, right? There's 4 number we can represent for 2-bit, and for this we can represent 1 point, like all 0 to all 1, right? Which is 8 numbers in total. And anyways, this range is larger than the fixed point. And the sign we can represent positive and negative. And for this side, we can represent this only for positive, like positive 1.2 10 to minus 38 to 3.4 10 to the 38. This is for positive, and for negative we can also represent okay, maybe this is clear. So don't forget, we always get a sign bit at first, and this is all the numbers range we can represent with 32-bit floating point representation. Yeah, is that clear?
Yeah.
Okay, so we goes to this figure here. And actually there's a gap here. And why is a gap here? I'm gonna tell you later. Okay. So just remember that there's a gap between around 0, which is a little problem. We're gonna fix this later. Yeah, and I already mentioned that we use bias encoding for exponent here, right? So if we got a 32-bit binary number, which is a floating point, and we can change it to decimal through this formula, which is the sign bit is here, which is positive or negative, and 1 is for default plus significant here, which is 23-bit, and exponent here, and bias encoding is just subtract 127, and we got the decimal number, right? Yeah, is that clear?
Yeah.
Okay. So we just say that we like for the exponent we got minus 127 to positive 128, which is the bias encoding of 0 to 255, right? And we do not use the first one and the last one, which is we do not use minus 127 and positive 128, and because we so minus 127 is 0, positive 128 is bias encoding of 255. So yeah, this is 0, this is 255. So we actually use, so this is the 0 here. This is a 255 here. And we use them for other specific usage, okay? We save them for other specific usage. And for 1 to 254, they are just a normal floating point we just discussed, like positive and negative, like floating point numbers. And for the first one and last one, for exponent number, we have specific use, and there's a sign before that. We ignore that, yeah. So this is sign, which is 1 bit, this is exponent, which is 8 bit, this is significant, which is 23 bit. And this is the thing we want to represent, which is the object, okay? And so we have not represent 0. 0 is just, so remember we set the 1 point plus plus plus, so 1 is for default, so we cannot represent 0 through this line, right? So we do 0 here. So if the exponent is 0 or minus 127, and the significant is 0, and we just like say it's 0. So you should like get like some idea of the representation, like just people like formalize a method to represent all the things, to use all the bit to represent all the things. That's invented by human and unified by humans. So all the computers use the same method to represent all the things. Yeah. So human being just say, so if the exponent is the smallest one and the significant is the 0, we just say it's 0, okay, here. And if like the exponent is 255 and significant is 0, so we just say it's the infinity. So we also got the sign here. So we got two zeros here, which is positive 0 and negative 0. And here is positive infinity and negative infinity. Right, is that clear?
Yeah.
Yeah, and so when we got infinity, like somehow if you divided 3 by 0, it's positive infinity. Yeah, and minus 3 divided by 0 is negative infinity. Yeah, that's very easy. Yeah, so there are still two other things we do not represent yet. We do not use yet, and we do not waste any bit, right? So we're gonna use them. And so significant, there are 23 bit in significant. So we actually can represent 2 to the 23 things. And for here, we only use 1, 0, and there are also all the other 2 to the 23 stuff we haven't used. So what do we, like, how do we use them? So for if the exponent is 255 here, and the significant is non-zero, we represent it as non, which is not a number, NaN or not a number. If you use Python before, Python, and you may got some like error or bugs which say something like a non. So this is like, because in computer we say that 3 divided by 0 is valid, it's it's positive infinity. This is valid. So how about 0 divided by 0? So this is not like this is invalid in math. Okay, maybe in math it's invalid, and so we just say it's not a valid number. Or also if we like scored is the 根号, right? And if we scored like -4, this is also invalid in math. So we just say it's another type of not a number or not. So there are a lot of types of not a number. Yeah, this is type 1, this is type 2. So we got a lot of types. So we just use all the non-zero here to represent different types of not a number. Okay, is that clear?
Yeah.
Okay. And we use all the things except this line. We're gonna use it to fix the gap between around 0. Remember, there's a gap around 0. Okay. Okay. So the number around 0, which is very small, we call them denorm. Yeah, the gap around 0 is called denorm. Just remember this name first. And we're gonna use this line to fix the denorm. Okay, and so firstly, why is there a gap around 0? And so this is odometer, and like if we say remember that we say the like smallest number is this 1.000 and multiply 2 to the minus 126, which is the smallest number. And so what is the second smallest number, like, which is 1.0001 multiply 2 to the minus 26. This is the second smallest number, which is have 1 here. Is that clear?
Yeah.
Okay, and so this is basically 2 to the minus 23, and we do that and we get this. So you see that the difference between the smallest number and the second smallest number is you just subtract b minus a is 2 to the minus 149, right? This is the difference between the smallest and the second smallest. But from the smallest to 0, it's 2 to the minus 126, right? And also for the third smallest to the second smallest, it's also 2 to the minus 149. Is that clear?
Yeah.
So there's a gap. So this is much larger than this, right? There's a gap around 0. Like basically this is 0, and this is the smallest number, which is 2 to the minus 126. And this is the second smallest. This is third smallest. And we go all the way. So there's a gap around 0. Can you understand why there's a gap now? Can you hear me? Hello?
Yeah.
Okay. Okay, this is kind of difficult part. And so how do we fix the gap? So remember that here we still got exponent equals 0, significant equals non-zero. We can still represent 2 to the minus 2 to the 23 things, right? And so we're gonna like just fix the gap. Okay, so firstly, why do we have this gap? It is basically because we set the 1 for default here. That's the reason why we have a gap. And so we just use this part to represent the denorm numbers, which is numbers in the gap. And so how to fix the gap? We just want them to be the same difference all the way to 0, right? So this is 2 to the minus 149. We want them to be all the way to 0, which is all this value. And so how many numbers do we need to represent to fix the gap? So this is 2 to the minus 126. It's divided by the step size, which is 2 to the minus 149. And we got 2 to the 23. So we basically need 2 to the 23 numbers to fix the gap, only for positive side, right? And we see here there are 2 to the 23 numbers we haven't used. So you're gonna use this to fix the gaps. Is that clear?
Yeah.
Okay, and so in this way, like if we have exponent is 0, or for the Bayesian encoding is minus 127, and all the non-zero significant. So in this way, we just say so human just make this rule. Okay, so if exponent is 0, then we set the exponent for default equals 1 minus 6 minus 126. Okay, and all the non-zeros still represent the stuff. And we do not have the default 1. We have default 0 here. And all the non-zero, all the significant also is still the same. Like here is all the significant 23-bit. And we have default 0 only for here, not default 1. And exponent is always minus 126. Okay. So what we got here? So no leading 1 or no default 1 is default 0, and there's 23-bit and multiply 10 to the 2 to the minus 126. So in this way, for the denorm numbers, we can represent all 0 to all 1, right? And this positive side. And for the all 1, it's basically 1 plus 1 minus 2 to the, remember this, and so we do not have, it's 0, it's 0 for default here, and this part is 1 minus 2 to the minus 23, and multiply 2 to the minus 126. This is the largest number in the denorm part, and the smallest number in the denorm part is basically it's basically this stuff. Okay, this is 0, and if we have 1, which is 2 to the minus 23 here, right? And multiply 2 to the minus 126, which is 2 to the minus 149. And this is the smallest number in denorm. This is the largest number in denorm. Is that clear?
Yeah.
And so in this way, we have the smallest number, which is 2 to the minus 149. And if we do not use the denorm, the smallest is 2 to the minus 126. So now we fix the gap. So we have this now, right? And the second smallest is 2 to the minus 148. Their difference is 2 to the minus 149, which is step size. So we got this. So there's no gap between around 0 now. This is very complicated. Can you understand this?
Yeah.
Okay, I hope so. Maybe you can go over the slide again to understand that. It may take several times. Okay, so anyways, we have the denorm here to represent, and we basically use all the 32-bit very well. And this is called IEEE. This is called IEEE 754. So all the computer like things around maybe 1997 all use this to represent like numbers with a point inside. I don't know how to say 小数. Okay. Okay, so this is floating point. And this is invented by a professor from Berkeley, and he won the Turing Award. So Turing Award is the Nobel Prize in computer science. Okay. So I have write a lot of other things to like go over the floating point. Like finally, what time is it? Okay. So we're gonna like go over the floating point again from 0 to positive infinity. Okay. So basically we have this odometer, which is 0 here. This is minus infinity. This is positive infinity. And I'm not showing you this. And for the other side, it's the same. Okay. So it's just changing the first sign bit. Okay. Yeah, so I just show you the positive side. What color to use? Maybe this color. Okay, so firstly, we have 0. If the exponent is, so see here, 0. So we have 2, 0, and we do not fix it as the negative numbers part. We just have 2, 0 in floating point because it's so powerful. And 0, so for 0 is significant equals 0, exponent equals 0, and we get 0, right? And we always set a sign for positive for now. And what is the smallest number like after 0? So it's exponent equals 0, all the significant equals significant is 0, 0, 0, 1. So this bit is 2 to the minus 23, and this exponent is 2 to the minus 126, right? If we have exponent 0 and significant non-zero here, and we represent the norm, which is for default, which is the exponent is minus 126, and the significant is 0.0 for default and something inside, which is represented by this 23-bit here. And so we got 2 to the minus 149, which is the smallest number. And what is the largest number in the norm? What is the second smallest number in the norm? So basically, this is still the same, and here is 0, 1, 0. Can you understand this?
Yeah.
Okay, 0, 1, 0 is the second smallest number. So this is the 2 to the minus 22. And let me think. Yeah, so basically, so we got oh yes. So we multiply them and get 2 to the minus 148, which is the second smallest number, right? And this is basically the smallest number plus the step size here, which is the 2 to the minus 149. What is the step size? It is 2 to the minus 23 here. Here is 23 bits, so 2 to the minus 23 multiply the exponent, which is 2 to the minus 126, and we got the smallest step size, and then we got the second smallest number. So basically from 0 to 2 to the minus 126, the step size is always 2 to the minus 149 here, right? And this is the smallest number. This is the second smallest number. Their difference is the step size is 2 to the minus 23. No. The 2 to the minus 149, which is the smallest step size. Is that clear?
Yeah.
Okay, that's kind of crazy. So remember that we can represent 2 to the 23 significant here. And so basically we can represent 2 to the 23 numbers, or 2 to the 23 step size, right? How do you say that? So basically, if you have, let's do a simple one first. If we have 2-bit, which is 1, 0, 0, 0, 1, 1, 0, 1, 1. So you got step size. This is a step size. So we got 3 step size here. And basically this is 2-bit. And for 23-bit, we got 2 to the 23 step size. So 2 to the 23 step size steps. Sorry. Oh God, this is so difficult. So 2 to the 23 steps, and the step size is 2 to the minus 149, right? And with this step, and from 0 to the minus 126, there, and between these two numbers there are these steps, and the step size is 2 to the minus 149. Is that clear?
Yeah.
Okay. Yeah. Okay, so now we go to 2 to the minus 126, which is the first number like out of the denorm part. And okay, this is smallest number, so we go to this area, right? This is the first number in this area. and which is here exponent becomes 0, 0, 0, 1, which is 2 to the minus 126. And here we got the smallest number, which is 0. And multiply them, we got 2 to the minus 126. And so what is the second smallest number in this in this part, in this line? What is second smallest? So basically we got this to 0, 0, 0, 1. And remember that for here we got the 1 for default, right? And so we just multiply them and we got 2 to the minus 126 plus 2 to the minus 149. Yeah, and this is the step size. Step size is calculated by 2 to the minus 23 plus multiply 2 to the minus 126 here. And this is the second smallest number in the outside the denote part, which is in this line. Yeah, so you see that the step size is, so from this number to this number, the step size is also 2 to the minus 149. Is that clear?
Yeah.
Okay, so, and if we go to like this, the next exponent part, which is 2 to the minus 125 here. Okay, so we go all the way from this to this. So there are 2 to the 23 steps. There's always 2 to the 23 steps because we have 23 bits, right? And the step size here is 2 to the minus 149. Okay. Yeah, so we go all the way to this number. Is that clear?
Yeah.
Okay. And since this number, the step size is going bigger and bigger. Okay, let me show you. Okay, and so this is the smallest number for exponent equals 2, which is 2 to the minus 125. And for here, the second smallest for exponent equals 2 is, yeah, basically this, and we got this. So here the step size is 2 to the minus 23 multiply 2 to the minus 125. Okay. And this is the step size here, which is 2 to the minus 148. So this is a lot. This is like larger than before, right? And so basically, from 2 to the minus 125 go all the way to 2 to the minus 124. The step size is like the step size is bigger, and there's also 2 to the 23 steps. The steps is also this, it's always this number, but the step size is going a little bigger. Okay, is that clear?
Yeah.
Okay, and we go another way too. If the exponent equals 3, then we go from 2 to the minus 124 to 2 to the minus 123. This is also equal 3, and just show you the smallest number here and the second smallest here. So the step size is 2 to the minus 147, which is again larger than this, right? Yeah. Okay, is that clear?
Yeah.
Okay, so now we go a long way, and we go to here exponent is equal to 127. So remember that the exponent is a bias encoding, so 127 basically means it is 0 here. So bias encoding, the bias is minus 127, right? So here is 2 to the 0 here, and for this exponent, the smallest number is 1 here, and the second smallest number here is 1 plus 2 to the minus 23, And here the step size is already 2 to the minus 23, so we go all the way to here. So basically from 2 to the 0 to 2 to the 1, which is 1 to 2, right? The step size is this, and there are also 2 to the 23 step size. Steps, yes. And similarly from 2 to 4, there are also 2 to the 23 steps, and the step size is going larger again from minus 23 to minus 22. Is that clear?
Yeah.
Okay, so we go a long way, and we go to the exponent equals 115. So basic coding minus 1 to 7, we got 23 here. And the smallest number for this exponent is 2 to the 23 here. And here the step size is 1. Okay, basically the same calculation, right? And so basically from 2 to the 23 to 2 to the 24, this is very large numbers. And if you want to represent like such large numbers, you need like a larger step size, which is very straightforward. And there's always 2 to the 23 steps, and for here the step size goes to 1. Okay, is that clear? Like 2 to the 0 is 1.
Yeah.
Okay, so similarly, this is the largest exponent here in this line, right? 254. And the largest exponent, and you just minus 127 and get 127 here. And we got the smallest number in this exponent is 2 to the 127. And to the second smallest, here the step size is already very big, which is 2 to the 104. And also 2 to the 23 steps. So from 2 to the 127 to 2 to the 128, the step size is 2 to the 104. Okay. Is that clear? This is the largest part.
Yeah.
Okay, and then we go to this line, which is 225. Sorry, this should be 255. Oh no, this is 254. No problem. And this is basically I'm showing you the largest number that can be represented by floating point, which is this. Yeah, you remember that we get this before, like from the range part, which is here, right? The largest number. Okay, and we got the largest number here, and when we goes to 255 and this goes to 0, and we got infinity, which is positive infinity. And if it is non-zero, we store all the non here. Okay. Is that clear?
Yeah.
Okay, and for the sign bit, if it's set to 1, so all the things are the same for negative part, except here we do not use non, we use the denorm for negative part, right? Yeah, so that's the crazy floating point. So I'm gonna give you a high level. So you see this, so you kind of like you can understand this odometer here. Like starting from around 0, the step size is the same, the smallest, and when we goes bigger and bigger, the step size also goes bigger and bigger, and we goes to infinity finally. Yeah. Yeah, so basically when we represent 0 to 2 to the minus 126, the step size is 2 to the minus 149, and from minus 126 to minus 125, the step size is also minus 149, right? Let me see. Yeah, that's it. And from minus 125 to minus 124, the step size becomes minus 148, and minus 124 to minus 123, that goes to minus 147. So start from this part, the step size is going larger and larger. So you can represent very accurate, like small number here, because you have all the step size between the small numbers, so you can represent very accurate small numbers. But when you goes to very big numbers, like basically like 10 plus 2, like this very big numbers, your step size goes very big. So for big numbers, the step size is very big, and it's not that accurate, because yeah, that's very okay, because for very large numbers, you just do not require it to be very accurate. But for like the number around 0, you must be very accurate about it, right? So the step size is going larger and larger. Yeah. So this odometer is like the summary of the floating point. Can you understand this?
Yeah.
Okay, that's difficult. So when I first learned this, I just go over the lecture several times to understand this. Yeah. But that's very beautiful, right? That's great ideas. So in computers, you sometimes got some bugs. Like basically computers, when you add 0.1 plus 0.2, you may got something like this. Yeah, if you use Python, you may got something like this. And like if you print, I think print 4.0, it may sometimes get you 3.999. And if you have learned the floating point, you're gonna know why is this. And also in computer, if x is a very large negative number, y is a very large positive numbers, and z is 1, and you first add y and z, because it's a very large number and the step size is very large, so you cannot take a small number such as 1 into account. So this in computer science, this is equal to this. So the 1 is just ignored, and you add them, you got 0. But if you add them first, and you got 0.0, and this is a small number, and they have small step size, and so in this case you can add them, and you got 1. So these two are not equal. So these like strange problems are all because of the floating point. But floating point, because it can represent so large range, it can represent very large numbers and very small numbers in just 32 bits. It's so nice, so people just take it. Yeah, is that clear?
Yeah.
Okay. So that's all the things, maybe.